Free body diagrams. The free body diagram is a critical part of any physics analysis of any situation. Every teacher and professor of physics that I've ever had has stressed the importance of the free body diagram, or for short, the FBD. And the reason it's important is it's the starting point of every solution, and it allows you to have a visual picture of what's going on. And without it, you will easily get confused and get mixed up. And so every year I still see students who choose not to draw a picture, and they come up for help, and I say, where's your diagram? Where's your FBD? And I didn't draw it, sir. And my question is, why not? Because it is a critical part of your solution. So what is a free body diagram? It's a very simple picture. It's a simple picture that shows all of the forces acting on an object. All of them. Now I get students who say, I'm not a very good artist, sir. I can't draw pictures. Now let me show you how good of an artist you have to be in order to draw free body diagrams. I will draw for you a car. Now I will draw a bus. And look, here is a snowboarder on a hill. And here is a chickadee. I can also draw a lion. I can draw a planet in outer space. And I can draw an ant. You see, all you need is a box to represent the object. You could use a circle. You could use any shape, really, that's simple to draw. And in fact, if you were an artist and you wanted to draw a little picture of a car that would help you, then you could do that too. But to save yourself time, a simple box will do. I like to use a box because a box has 4 definite sides that really make it clear which way the forces are acting. So our object in the question is simply going to be a box. And once you draw the box, you then decide what sort of forces are acting on the box. Maybe there's a force of gravity. So you can put the arrow here and identify the force of gravity. Now forces are vectors. So to remind you how that works, when we draw a vector arrow, we can use the length of the arrow to show how strong or how the magnitude of the force is expressed. Big force, little force. But on a free body diagram, I find that if you start drawing little arrows and big arrows, it gets confusing. Some arrows are too small to work with, some are too big. So another way to do it is to draw the arrow, give it a label or a name, like I did here, force of gravity. And if you know how much the magnitude is, simply write in the magnitude beside the arrow, 40 newtons. Then we don't have to worry about long arrows and short arrows. So you can express the magnitude with a number beside. Now let's say that there's also a person who's pulling this way with a rope. Well, people who pull on things are applying forces, so I like to call those kinds of things force applied. And maybe they're pulling on the rope with 300 newtons. But maybe this rope is also being pulled this way by someone else. So if there are more than one person pulling, we have force applied 1, force applied 2, and maybe this force applied is 30 newtons. And who knows, there could be 1,000 forces acting. Maybe this box is actually sitting on the ground. And if it's sitting on the ground, we learned in our previous videos that the gravity pulling down is the action force, and the reaction is the ground pushing back up. Maybe there's a normal force. And if there's a normal force, we also learned that normal forces represent the force between surfaces. And the force between the surface might cause friction. And so perhaps we would need to add a frictional force. And the frictional force might be acting against the motion, and this could be the friction force, force of friction. And you could label it, or you could figure it out. Sometimes we know the numbers for sure where that came from. Sometimes we know the numbers we need because the question tells us. Other times we don't. So we leave them like this and we draw them all in. Now this is a fairly complicated free body diagram. Most of the ones you'll start with are much simpler. So let's just do a couple of simpler examples. Let's take a scenario of a book on a table. A book on a table. Well, a simple picture. And here's my book on a table. The other nice thing about a box is inside the box you can often write what the mass is going to be, because mass is an important number that we tend to use a lot, but we'll worry about that later. All right. What would be the forces acting on a book? Well, the one force that's pretty hard to escape is gravity. There seems to always be gravity. So we could write Fg. And of course, if there's gravity and you have a surface, then the surface will push back and there will be a normal force. If the book was just sort of falling through the air, then there would be no normal force. You can't have a normal force without a surface to push back. Now let's think if there might be anything else. There's the book. It's sitting there. No one's pushing it. No one's pulling it. What about friction? Is there friction between the book and the desk? I mean, there's certainly a surface here, and it's touching, and there's certainly a force pushing them together. However, you should remember that friction is like a reaction force. Friction is a reaction force. In other words, it doesn't turn on unless you try to pull something. So it reacts to an applied force. So technically, there really isn't any friction unless you try to pull something. Because if there was, in this case, if there was a force of friction, how would we know which way it was going? And if it was going, let's say it was going this way, then wouldn't that cause the book to suddenly fly off to the left? Newton's law says it would, because there is a force to the left that's not balanced by a force to the right. And that should cause an acceleration. So technically, there's no frictional force that needs to be labeled because nothing is trying to move this block. So that's the simple picture. That's all there would be in that free body diagram. Some can be even simpler than that. Let's talk about the book falling through the air. Here's the book. It's falling through the air, right? Now, we won't put those in the picture because it confuses our arrows. But we know it's falling from the air. What force would be causing it to fall? Our good old friend gravity. Very hard to have a force picture, a free body diagram without gravity. What other forces might there be? There might be another force that's very small. I'll put it here, and I'll put a small arrow. This would be the air resistance. The air resistance. We all know that as you fall through the air, it holds you up. There's a friction with the air. Now, not the fair resistance, but the force of air resistance. The air resistance is usually, for falling objects, fairly small. Fairly small. So we might not even include the air resistance at all. If you were a tiny, tiny object, like a speck of dust, then air resistance could be a very significant force for you. But if you're a book falling through the air from, say, the top of a roof or even from the tabletop, then the air resistance isn't really going to affect your motion all that much. So it's possible that this free body diagram might not have anything but the force of gravity on it. And that's all there is the force of gravity pulling this book down to the ground. A very simple free body diagram. A more common free body diagram would be a block for, let's say, your car. Well, your car would have on the ground a force of gravity, and of course then that means that the ground would push up with a normal force. And that's good. The forces are balanced up and down, so the car doesn't fly into the air, nor does it sink into the ground. It does just what it should. It stays there. But your car has an engine that might be providing a force that's causing the car to want to move this way. Well, the car's engine is applying a force, so it's the force applied. Then, of course, what would be trying to stop you? Well, good old force of friction between the wheels and the road. And maybe also some air resistance. So you might have a couple of arrows here. But as I said, air resistance is something that we tend to ignore, especially when we're beginning in physics, because it's very complicated to figure out, first of all. Air is a very ununiform substance. It's got hot spots, and cold spots, and dense spots, and not so dense spots, and sometimes it's rising, and sometimes it's sinking and moving, and it creates a problem for us to figure out what the air resistance actually would be. And as I said, for big objects that are not falling that fast through the air resistance is so small it's not even worth thinking about. So this picture might be the free body diagram that you would draw for a car driving down a road. And you could draw a free body diagram for all kinds of things. Another common one that comes up in physics a lot is the elevator. So we have an elevator. Well, what's on an elevator? Gravity is trying to pull the elevator down, and there is no surface to push up. A lot of students, when they start with elevator problems, they say, okay, there must be a normal force, because I did that on all my other pictures, but they didn't remember that the normal force is only there if there's a surface pushing up. Without a surface, you can't have a normal. So, what is the force that might push up from an elevator? Well, most elevators have a cable of some kind, and the cable has a force. The force of the cable is pulling up on the elevator. And that would be it. There wouldn't be much else happening on an elevator. It only moves up and down. It has no sideways motion whatsoever, so it doesn't matter what's happening on the sides. And the force of a cable is sometimes called the tension. The word tension is really just a fancy word for force in a rope or cable or string. A string, a rope, a cable. In fact, anything can have tension. Tension can be at a concrete beam, or a concrete block, or a steel beam. Tension can be in a piece of wood. Your body can experience tension. But typically in free body diagrams in physics, forces that are caused by strings, ropes, cables, and things like that are frequently called tensions. But tension is just another word for force. And so you can call it FC, you can call it tension. Sometimes we put a T there instead, but a T equals an F. And so you can use a T to represent the force in a rope in any of your free body diagrams and any of the net force equations that we will begin to develop shortly. And so that's just another word that pops up, tension. It's simply just a force that occurs usually in a string or a rope or a cable, or a chain or anything of those sorts. So free body diagrams, very critical, very important.